Hi, everyone. So we're starting chapter 4. We only have 4 sections of the unit, so it's a smaller chapter. So hopefully we can get through it with an extra day or so to head into chapters 5 and 6. So we're looking at the instantaneous rates of change of sinusoidal functions. So again, sinusoidal functions are our wave curves, which would be, we're looking at the sine function, which is right here, and we're looking at our cosine function, which is right here. And again, that's back to, we started that in grade 11. And what else did I want to point out here? So the tangent curve is not sinusoidal. So again, we're only looking at the sine and cosine function. So what we're going to do is look at our key points and their rates of change. So again, we're looking at the rates of change to draw our derivative curve here. So if I were to look at, let's say just trying to see what color here. Hopefully you can see this purple. If I were to start here along my sine curve at the origin here at 0, 0. So again, these are my x values. These are the degrees, right? Which you may have seen in grade 11. From the grade 12 functions course, these are our radian values, right? So if you don't know that, again, I can show you how to do everything just by converting it to degrees. So just know that pi is 180, right? 2 pi would be double 180, 360. Half of pi, right? Pi divided by 2 is half of 180, 90, and so on. Or you could just memorize, these are the only really important values we're going to be looking at, 4 on the right, and let's say 4 on the left along the x-axis. So if we were to look at this 0, 0 here, this x value of 0, if I were to draw my tangent line, and again, I'm just gonna kind of do a rough job. The point is that, again, that it would be positive, right? We're increasing along this point. The tangent line would be positive. If I were to calculate the slope of that tangent line, just to tell you, it actually would be 1. So for our derivative function, the derivative at that point, we're going to say is 1. We're going to go up here to 1 and place a value of 1. If I were to look at my tangent line here at this turning point, right? So there's my point of inflection. Here's my turning point. So we have 1, 2, 3, 4, let's say turning points. What would the slope be there, right? The tangent line is horizontal. Again, whether you want to write that down or not. So my slope would be 0. So if my slope is 0 for my derivative function, I'm going to make it equal to 0 along the x-axis. So let's just go to all our turning points then. So this turning point here, horizontal line, slope of 0, place it at 0. This turning point here, this minimum value is, again, the tangent line would have a slope of 0, place it at 0 for my derivative function graph. And then this turning point here, which is a maximum, has a slope of 0, and same thing. So now I have, well, technically 4 points along my derivative curve that I want to graph that are at 0, and we've done 1 here, point of inflection tangent line, which is up at 1. So let's do another one. Let's say this point here, where I have the point of inflection where I'm now on the decrease, I'm decreasing, and if I were to draw this tangent line in, it would be a negative, right? Slope. And if I were to calculate that slope, just to make things easier, I can just tell you that slope would actually be calculated to be -1. So let's put that value at that point of inflection there. For the derivative would be at -1. So we see here I'm along -1, which is also the same, right, minimum point that it was from the original graph. This is the same maximum point, local maxima, that it was from the original graph. That's not changing, just where it's at along the x-axis is changing. And then I have another turning point right here, which is positive. So again, that slope would be positive, +1. Just follow, we've done all of our turning points, just follow where your points of inflection are. This is an inflection point, it would be negative, so then it would be at -1. And if it's positive, I know that my slope would be positive, and I just know that it would be either +1 or -1. So if it's positive and I'm going up, it's +1. And that would be my starting point along this. So I'm going to do my best. I'll make this a little thicker. Again, really the goal is that you do a better job than I do, because it's harder on the tablet here. So I am decreasing. I am increasing. That should be looking more curved, decreasing, then change it to increasing. Again, it should look, this should look more curved, not so much of a straight line there. More curved. And this is my derivative graph. So yellow, I don't want to write it in yellow. I'm just going to write it in brown. This is the original y equals, I'm too thick here, y equals sine x, right? Says this is the yellow curve is y equals sine x. We just talked about all the properties of the sine curve. And so if we look at the derivative, what can we conclude here? So if my original is y equals sine of x, what can you conclude about the derivative of the sine? Y prime, the derivative is going to be, what do you notice? I'll change that back to purple. Starting at 1, going down to -1, 1, -1, what curve looks like this? That is exactly the cos curve, actually. Now, it can't be looking like, it does have to be that exactly at negative pi, it's at -1. Exactly at 0, it's at 1. But if you were to compare it, which is actually the graph just down below, so if you've printed out your sheet, right, just look at the graph down below. So starting at -1, starting at +1, going down to -1 for negative pi, up to 1 at 0. If I were to move down here, again, I'm just going to leave this up for now. So I'll do it here, right? Starting at 1, going to -1 again at negative pi, back up to 1 at 0. It literally is exactly the cosine curve. So there's one thing that we know now. The derivative of the sine curve, the derivative is exactly the cos curve. So now let's take a look at the derivative of the cos curve and see what that would be. You might have a guess. Let's see if that's correct, that guess. So going now to, whoops, just to move. Investigating the derivative of y equals cos of x. So this graph is y equals cos of x, which is in blue. So I can write that out anywhere here. I don't really have to write it out, but just to know that this part here is y equals cos of x, my original function, right? So if I'm looking at the derivative, I'm going to do the same thing. Why don't we start at my, let's say, turning points, right? So here I have a turning point where my tangent line is horizontal, a horizontal tangent line, slope of 0, place it at 0. Horizontal tangent line, 0, slope of 0. Horizontal tangent line, 0. Horizontal tangent line, 0. Horizontal tangent line, 0. So we've got 5 places here on my derivative function. I don't know exactly what it's going to look like yet, but looking at the turning points of where it's 0 along the x-axis. And again, these radian values and degrees are exactly the same as they were for the sine curve, right? Which makes it easy to memorize if you wanted to. Now my point of inflection, here's a point of inflection here. I'm decreasing. So if I were to draw a tangent line, it would be negative. So if it's negative, I know it has a slope of -1. I go to my next point of inflection, which is here where the twist is, and it would be positive. So I'm at +1. The next one here, right, would be negative tangent line. So if it's negative, again, if I calculated the slope of that line, you can go ahead and do it, but just for time's sake, you would get a slope of -1. So on the derivative curve, I'm placing a point at -1. Here's a positive point of inflection, so it's going to be +1. And again, when I draw my graph in, debating, should I go thicker like last time to do a better job? So far, not too bad. Yeah, not too bad. Should be a little bit more curved. Again, this graph would be, well, we're not sure yet. The derivative graph, that's what we're going to talk about. So let's be careful here, because you might, okay, let's do some observations here, right? Doesn't it look like starting at 0, right? Going down to -1, up to 0, up to 1, sorry, then starting at 0. So there's my period. We'll talk about that in a future video. right? There's my cycle going from -1 to +1, starting at 0. It looks like sine, does it not? So you might think that it looks like, but again, absolutely double check because it's actually not quite sine. So if we take a look starting at the origin, so I'm just going to move up to my sine curve there, right? To show you here. So again, just take a look at the yellow, or go, hopefully your handout is printed. If I'm starting at the origin and moving to the right, the graph for the sine curve is going up. So from the origin, I'm going up to 1, then to 0, then to -1. So let's go to ours that we think is sine. Look at the black graph. When I do the derivative of the cos function, I'm starting at 0 at the origin. What's happening? I'm not going up, actually. I'm going down to -1, then back to 0, then up to 1, then down to 0. So it's basically similar, but what I'm actually doing is the reverse of the sine function. So just to write out here, what do you conclude about the derivative of the cosine function? How thick am I here? If I have y equals cos of x, my derivative, I don't know what color we want to do that in, my derivative is not quite sine of x, but the reverse of sine of x, instead of going up, I'm going down, is actually negative out in front, sine of x. So we're actually reflecting it over the x-axis. So if you go back to grade 11 again, when I have a negative in front, or even grade 10, if we look at quadratics, when the negative is in front, it's flipping it over the x-axis, a reflection in the x-axis. So again, if you wanted to write that down, we're reflecting the regular sine curve reflection in the x-axis, which is why we have a negative out in front. So the derivative of the sine curve is exactly cos, our conclusions for this lesson, and our derivative of the cos curve is the sine curve reflected in the x-axis, so just negative sine of x. And that's all we need to know for this part of the lesson.